as Williamson ether, right? SN2 attack, making that thiolate, so just like an alkoxide, except an S with a negative charge, right? You get that primary leaving group, and then there you can link those two R groups together with that S. Right, still an SN2 attack. So, right, let's see. Yeah, and then another similar reaction is instead of Williamson ether is the alcohol condensation. Right, you still have these two alcohols, but instead of making one the alkoxide and one the tosylate, right, you just add H2SO4 and heat. Right, these H2SO4, the H2SO4 will provide a proton to one of these alcohols, right? These alcohols are, think about it, they're also bases. So they're going to accept that proton over there, making one of them a good leaving group and one of them a being the nucleophile. It's going to be a weak nucleophile reaction, so it's it's similar. It's still going to do a substitution attack on the other alcohol, linking those two R groups together. Right. Right. Another one, but this is kind of like a review from OCHEM 1. You have your alkoxymercuration, demercuration reaction. Right. You have your HGOAC2. Right. With the R group that you want to add. This NaBH4 is just to remove that mercury compound. Right. So the mercury will attach to one of the alkenes, right? And your R group or your R alcohol group will attach on the other side, and then the NaBH4 just removes that mercury group. Remember, the alcohol will attach to the more substituted carbon. So if, let's say, this was the carbon on the left is a tertiary, and then the carbon on the right is secondary, right? The alcohol will attach to the tertiary side. So, next. Right. Another review is the formation of the epoxide. So using MCPPA or any peroxy acids. Peroxy acids, remember that's when you have three oxygens in formed kind of like this, where you have a carbonyl group, right, linked together by two oxygens in series, and it will create that epoxide. Now remember, it will only epoxide the most substituted alkene. So here, this molecule, you have two alkenes, but the one on the right has more substituents, so you'll have your epoxide there. And remember, it adds to the alkene on the same side. So if you had substituents on that alkene, they will stay in this, they'll be in the same stereochemistry, kind of like what we have in the CH3 here. Now, another way you could make an epoxide is the halohydrin cyclization. Right, so you have your alkene, you have your H2O and chlorine water, basically. Here, this is different in that you make a kind of like an epoxide, but with the halogen right here. And this it's an intermediate step where the water will attack one of these carbons right here and open up that ring, giving you the OH and the Cl. And then now, if you react an alcohol right? It will deprotonate this H, making an epoxide. And remember, epoxide or any ethers, you need a good leaving group and an alkoxide. Here we have a good leaving group right here, and we have the alkoxide. And when these two react, you have the intramolecular reaction, making that epoxide right there. So it's an internal SN2 attack. Okay, now reactions with epoxides and ethers. Right, you have the ether cleavage. Right, so if you want to split ethers, you can use a halogen or alkyl halide. So here we want to use a base, or not base, an acid. This acid will provide a proton to that ether. Now that ether now is positive charge. And from there, this becomes a good leaving group for the nucleophile, which was where the H was, to come back in and substitute one of the R groups right here. So that's how you would split an ether. You can use HBr, HI. It would add some good nucleophiles. The proton from the acid just makes the oxygen a good leaving group, so they can do a SN2 reaction, right? Now, the next one is with the epoxide, we want to know how to open up the epoxide. Right, so there's two ways of doing this. There's acidic conditions and the basic conditions. With acidic, the H plus will make the epoxide a good leaving group. What do you mean by that? The H will go over here, making that positive charge. Whenever an oxygen has a positive charge, it doesn't like that. Right? So it will want to take electrons with that oxygen. So here it steals it from this side, from the top carbon. Now, you might be wondering, why not the bottom side, bottom carbon, right? Well, when this epoxide becomes a good leaving group, it undergoes SN1 reaction. Remember SN1 versus SN2, SN1 is you have a two-step reaction where you make a carbocation intermediate. So to make a good carbocation, it has to steal from the top, because when you steal from the top, you have a tertiary. In here, you have a tertiary carbocation when you remove it. If you remove from the bottom, you get a secondary carbocation. So the most stable will be the top carbon. And then once you get that stable carbocation, you have that backside attack from that nucleophile, and which we will attach on the top right there. Okay, so that's acid. The second one is the basic conditions, where it doesn't care if the epoxide is a good leaving group or not. It will just attack it from the least substituted carbon. So just an SN2 attack, it will do attack the side that's less hindered, which is number 2 over here. And remember, it doesn't care if it's a good leaving group, it'll basically force its way in there. And then proper workup will turn this O negative into an OH. Right. So it's a faster reaction. It's a one-step reaction compared to acidic conditions. Okay. All right, so here's another overview. If you want your alcohol, when you open your ring towards the most substituted side, you would do the basic conditions. If you want to open up the epoxide on the least substituted side, remember to use an acidic conditions, like over here. Another way you can open up a epoxide is using a Grignard or organolithiums. right? Same concept where it will do an SN2 attack on the least hindered carbon. So kind of like a basic conditions. Here you just have, it will just attack the least substitute carbon, which in this case is the one on the left, right? Same with organolithiums. You can just treat this as R with a negative sign on it. The MgX is just there to show that it's the one that's carrying that R group. Okay. Okay. Now let's move on to chapter 15. Does anyone have any questions on 14? Okay. Now, chapter 15, right here is where you have your conjugated systems, you have your molecular orbital theory, and the homolumo stuff. You have your Diels-Alder, and then you have your UV spectroscopy. Right. So remember, conjugate systems, it's just double bond separated by a single bond. Right. They're very stable, right? Because you have that resonance keeping it stable. Right? And then so you have your molecular orbitals here. Now, yeah, these conjugated systems are, they are sp2 hybridized, meaning they have p orbitals that keeps them stable. Remember, those p orbitals have two lobes, one on top, one on bottom, like shown over here. And when those lobes line up together, you have that what's called a constructive interference, where you make a bonding pair, right? And when they don't match signs, that's where you have your destructive interference, where they kind of cancel each other out, and you will get a node or anti-bonding pair. Right, so kind of like this. So when you're drawing your molecular orbitals, remember the number of lobes you have equals the number of molecular orbitals configurations you have. So for here, butadiene, right? That's, if I were to draw it out, that is, no, it's too big. Yeah, like that. Anyways, so here you have your butadiene. You have 4 sp3 carbons, right? You have 4 sp3 carbons, meaning you have 4 lobes in your molecular orbitals. 4 lobes, that means you have 4 different types of configurations you could have. Remember, the highest energy is on top and lowest energy at the bottom. And your up and down arrows, how do you know how many arrows you're going to have? It's the same as how many pi electrons your molecule has. So butadiene, 2 double bonds, so that means 4 pi electrons. So you start from the bottom, work your way up to the top. Remember, there's maximum of 2 in each orbital. So you have 1, 2, 3, 4. That's how you can tell which one is your HOMO and LUMO. Right? HOMO means highest occupied molecular orbital, and then LUMO is lowest unoccupied. Right? Highest occupied just means the highest energy that has electrons on it. So even if this is just 1, it's still a occupied molecular orbital. LUMO is if it doesn't have any, right? Okay, and then remember, the number of nodes increase as you go up. The bottom one always has 0 nodes. Okay. And then addition reactions of conjugate dienes. Here is when you have that 1, 2, 1, 4 addition. Right, you have your kinetic which is the cold reaction, and then the thermodynamic control, which is the hot reaction. Right. The difference, we'll go over that, is so with kinetic control, remember that's 1-2 addition. It is where you have to form the most stable carbocation. Right. So step 1, form the most stable carbocation. So one of the double bonds will grab an H from, or a halogen if it's like a X2 compound, right? So the one of the double bonds will get that, and then you will get a carbocation. So here's an example. You have HBr. We'll choose this as the one that's getting the hydrogen, right? And then you still have your butadiene here, but we want our carbocation to be in the most stable. So here we have a secondary allylic carbocation, and that is pretty stable. So the Br will attack that once you form that most stable carbocation, and you'll have it on. You have that 1-2 addition. Right now, your thermodynamic control. Remember, it's 1 for addition. You still form the most stable carbocation, but the difference is you have to resonate that carbocation. Right? When you resonate it, you'll form the most stable alkene, and from there you attach the nucleophile to the carbocation. So going back here, the alkene grabs the H, and you have that carbocation, and then you resonate it. Remember to resonate it if it's hot. Once you resonate it, that Br can go to the resonated carbocation and add to it there. So that's your 1-4 addition. Yeah.
So with the kinetic, are you not going to resonate at all?
No. With kinetic, it's always the most stable carbocation. Once you resonate it, it's not a stable carbocation anymore. Yeah. Okay. All right. Now for the Diels-Alder reaction, right? So here you have that diene, and you have your dienophile. Remember, we want our diene to be electron rich. So electron donating groups, we want our electron donating groups to be there. Dienophile electron poor, we want our electron withdrawing groups there. Right? So it's a fourth sacral addition, which just means that you're going to make a ring with that double bond over there, right? Okay. All right, so if you were to rank these, remember we have to consider steric hindrance, and we want it to be open, or what do we call it, estis. Right, so for this one, going from the left, this diene cannot be on the same side, they cannot be cis, because this ring is keeping it from rotating. So here there will be no reaction. Now, as you go to the right, if you have your substituents going on the inner part of the diene, it's going to have that steric hindrance. Right, you want it to be on the outside, like here. If possible, you want it to be completely away from the reaction, like the fourth one. And then here, the reason why this is fast, right, because it's locked in that cis configuration. Right, and then if you add electron withdrawing groups, that's going to make it weaker. If you add electron donating groups, that's going to make it stronger, right? Because we want our diene to be electron rich. Okay. So going over the molecular diagram of this butadiene, right? So we have we figured out our homolumo, right? We have 4 pi electrons, so that makes this third, or the third from the bottom, the second from the bottom configuration to be the HOMO. Right, remember diene is the HOMO, well, and then while the NFL is the LUMO. It receives the electron, diene donates the electrons. That's why you want dienes to be electron rich so they can donate those electrons. Another thing we have to consider is the endo rule. So whenever we do our Diels-Alder, remember, electron withdrawing groups with pi bonds are endo. Endo means it's pointing away from you, so they will be drawn as dashes. Right, the reason why I say with pi bonds is if you have, let's say, CF3s, is it 3? Yeah, that's a 3, okay. CF3s. CF3 is electron withdrawing, right? Because you have 3 fluorines, which are highly electronegative, but they don't have any pi bonds, right? Pi bonds just means double bonds. So because it doesn't have double bonds, it will go in XO. Here. Other electron withdrawing groups, they are usually with pi bonds, like this aldehyde, right? You have that pi bond with the C and the O, and there will, because of that, it will want to be close with the other double bond. That's why it's endo. So it just helps stabilize it in that position. Okay, here's another one. The stereochemistry. Typically, people will usually professors use the one on the left side. But if your withdrawing group is drawn as a dash, right? The top and bottom will also be dashes, and then the inner side is the wedges, right? This is people call this the Duda rule, right? D down and U here is up, then down up. Now, if you were to make it a wedge, right, you would have to flip it. It's just the same thing as looking at it from the top and looking at it from the bottom, right? So if you want to keep it consistent, just use the one on the left side. Um, just make sure that your endo is a dash. Okay, another rule for Diels-Alder is you never form the 1,3 product. So when you have a 1,3 product, right, you should know immediately that that's wrong. So how you would do this is, if you have a donating group, right, it's going to repel electrons. But when it repels electrons, the carbon next to it will be positive, and then electron withdrawing groups will attract electrons. So the carbon right next to it will be slightly negative. And then what happens is you have to orient it to where they are opposites. So kind of like a magnet, they will form a bond together, and then you will have your product there. So similar to this one, this 1,4 product, your donating group will repel electrons. So this double bond will be repelled towards this carbon. So you have a negative sign over here. And then same thing for this withdrawing group, it will attract electrons toward this carbon, and this will be negative. And so they connect, and you have that 1,4 product. All right, so here's another one where you have to flip it. Here you have, for negative on the bottom and negative also on the bottom of the dienophile. But because they're not opposite, you have to flip. Here, you have to flip one of them. So in this case, you flip the dienophile so they could cancel out and make a bond. And then here's your forbidden cyclic addition, the 2 plus 2 or 4 plus 4. Right? The reason why is because one of them has to be the HOMO, one of them has to be the LUMO, right? So if you look at the HOMO-LUMO of this molecule, this one matches up, but this one does not. So the only way to make them match up is you need to react it with light. This will flip the HOMO orbital, and yeah, it'll basically make them actually match up. And then you would have that bonding reaction. Okay. Now, for UV spectroscopy, remember, we want more conjugation. So if we have 2 conjugation, that's better, or this is worse than 3. Right, you can see the numbers here. You have a higher UV max. You also want more substituents. So to figure out how many substituents you have is look at your conjugated system. How many substituents is sticking out of it? Here you have 2, right? 1, 2. And here you have 3. So this will be 1, 2, and 3. So that's why this one is higher than the ones with no substituents. Okay. All right, does anyone have any questions on chapter 15? You good? Okay. Now, chapter 16, here's where you have the introduction of aromaticity, right, in your benzene rings. Okay. Okay, so benzene, right? It's 6 carbons, right, in conjugation. Remember, they are 1600 in the IR. Benzene fragment is 77, and your HNMR for benzene is 7 to 8. And don't forget your exam 1 stuff, because most likely they will show up in your exam. They are sp2 hybridized. Okay. So ortho, meta, and para, right? The one next to the substituent, which is X here, that is ortho. So it's on this side or this side. Meta is the one after that, which is 1, 3. And para is the one opposite of the substituent. So 1, 4. Molecular orbitals for benzene. So if you were to write the molecular orbital, you use the polygon rule, where you kind of make the polygon of the molecule, where you have the vertex at the bottom. So the vertex is always at the bottom. And since we have 6 pi electrons, we go from bottom to top, we fill it up, and then here you would have your, this would be these 2 would be your HOMO, this would be your LUMO. So yeah, the vertex always on bottom, so as you can see over here. Number of arrows is number of pi electrons you have, and they always occupy empty orbitals first. So the middle, you have cyclobutadiene. You fill up the bottom one, we have 4 pi electrons, so we have 2 more. One goes in the left, one goes in the right. And that's how you define your HOMO-LUMO on cyclic structures. Okay. All right, so aromaticity. Aromatic compounds are more stable than non-aromatic and anti-aromatic. The requirements they have are they have to be cyclic, so they form a ring. They have to be conjugated, so like in this for this one, you have they're not it's not all conjugated. You have to be completely conjugated, and all atoms are sp2 hybridized. So this in our aromatic, does you have sp3 here, sp3 over there, and that they have to be flat. Now, once you meet those criteria, now you can use Huckel's rule. So that's when you do the 4n plus 2, which is 6 or 10, that's aromatic, or 4n, which is anti-aromatic, so 4, 8, 12. Right, you don't do Huckel's rule first and then do your requirements. Remember, you do your requirements first and then Huckel's rule. Okay. The one weird one is you have the 8-ringed cyclic structure. If you see this, you might think 8 pi electrons anti-aromatic, but no, this is non-aromatic because it is not flat. So depending on what your professor says, I don't know, sometimes they consider it anti-aromatic, but you can always argue that it's non-aromatic because it's not flat. Okay, so what if there's anions or cations? Cations just means there's no pi electrons on that atom. Anion means there's 2 pi electrons on that atom. Right, and so if we're ranking by basicity or acidity, remember the reaction will not occur or less likely to occur if it makes the overall molecule less stable. Just also remember that atoms with lone pairs, the neighbor sp2 atoms are also sp2 because those lone pairs can resonate. Okay, so an example is cyclopentadiene, which is like this one. Now, if we have a base and deprotonate this, now it turns into non-aromatic to aromatic. So that's good. That's favorable. Now, for this one, if we turn this into a good leaving group, so we dehydrate this molecule. If we dehydrate it, it becomes non-aromatic and turns into anti-aromatic. That's not good. So this will not occur. It makes it, dehydrating this molecule is less likely to happen, and so because it forms an anti-aromatic ring. Okay, another example here. We have 1, 2, 3, 4, 5, 6, 7, 8 on the left side. That's anti. And then here with cation, you have 6. So you have 0 here, 2, 4, 6, and you have aromatic. Yeah. All right, so remember, you have to make sure your requirements are met first before you use Huckel's rule. So here you would see, I see a lot of people just looking at this and say 2, 4, 6, aromatic, but you're not considering the rule first where they all have to be sp2. So this is sp3, so automatically this is non-aromatic. Here, all of these carbons are sp2, so 2, 4, 6, it is aromatic. Right, so going into basicity, right, this usually simply where you have your nitrogens. Remember, nitrogens have 2 have two electrons or one lone pair, right? Basically, it's just we have to rank it based off of how likely this lone pair can grab a hydrogen. And when it grabs a hydrogen, does it make the overall molecule more stable, less stable, or stay the same? Okay. We have to make sure the lone pair is not in the p orbital. Okay. So here, this nitrogen here has lone pairs. When we add the H, it goes from aromatic to still aromatic. So these lone pairs are basic. Now for this one, we have lone pairs here, but right now it's 2, 4, 6, it is aromatic. Now, because this lone pairs are in the p orbital, if we remove it from the resonance, now we have a non-aromatic ring, because now this is sp3. Right? So we're taking away from that resonance, meaning we're making it less stable. So this one is not likely to happen. So it's not basic. Okay. Yeah. So figuring out if this is basic or not. Remember, single bonds are p or on sp2 or sp3, and pi bonds are always in p orbital. So if for this nitrogen, the p orbital is already filled, so making this sp2. So that means this is basic. Same with this. Now with this nitrogen, you have 3 single bonds. So the sp2 orbitals are already filled, and your last one should be in your p orbital. Right? So because that's in the p orbital, it is not basic. Okay, does anyone have any questions on 16, chapter 16? Yep. Okay. Okay, so chapter 17, this is should be the last one for this exam. So here we're going to go over sigma complex. You have electrophilic aromatic substitution with benzene, same with nucleophilic aromatic substitution. Some other reactions as well. So sigma complex, right? Sigma complex, this benzene will take a electrophilic compound. So electrophilic, meaning it's positive and wants electrons. So this lone pair, or not lone pair, this double bond will grab the electrophile, right, making a positive charge on one of the carbons, which is the double bond that electrons just left. And so it's just the sigma complex is just resonating that carbocation. Like this. Okay. And then you have that base. That base will just grab that H, that is on the carbon that just took the electrophile, and you will have that elimination where you reform that double bond. Right, so adding bromine. Bromine, you just do Br2 FeBr3. Yeah, the FeBr3 is there to make Br2 a electrophile. So you'll have a Br plus. That Br plus will be attracted by this double bond. You have the Br, and you'll make this. Now to reform that double bond, that Br it just took will grab the H, reforming HBr. and making a double bond. Then chlorine fluorination, same thing, right? FeCl3 will turn this into Cl plus, and then forming the sigma complex, and then forming that double bond again. And then if you have excess chlorine with pressure, it will just add everywhere. So every single carbon will have a Cl. Okay, adding iodine, you just need half of I2 and HNO3, and that's there to add the iodine. So this is kind of like the weird one out where Br and Cl, you just add FeCl3 or FeBr3. Here you need nitric acid and half a mole of iodine. Now adding a nitro group is just HNO3 and sulfuric acid. Remember this, it's like these reactions comes in pairs. The other one of them is the electrophile, the other one is what makes it an electrophile. So this H2SO4 will turn this into an electrophile or more positive. And so yeah, it's gonna do this acid, sulfuric acid will donate a proton to HNO3, making this positive and making it attracted to one of the double bonds here, and making that NO2. And so if we want to make an H2 or amino group, we have to do nitration and reduction. You can't just add NH2 in the molecule. You add the nitro first, and then here we're using the Clemmensen reduction. So zinc HCl will turn that O2 to H2. Now sulfonic acid, that's just SO3 H2SO4, similar to the adding a nitro group. This H2SO4 will turn this SO3 into a electrophile and making it able to attach to the benzene. This is unique that you can use H2SO4 again to remove it, to remove that SO3 or the SO3H. Yeah. All right. So now if the benzene is substituted, the other reactions I just showed you, that's when benzene is just by itself. Now, if it's substituted, you have to look at the substituents. Electron donating groups activates it. It provides it electrons. And when it's activated, it is orthopara. Remember, para is better because it's less steric hindrance. Withdrawing groups deactivates it, meaning it's going to add to the meta position. Right? It all depends on the sigma complex. So wherever it is, so when you resonate that positive charge, it is where that positive charge is most stable at. Okay. So we have your activators here going from left to right. Remember, activators usually have lone pairs. Right? If you look at all of these, except for the last one, our groups are always donating. But everything else, they have lone pairs. And these lone pairs the groups here are able to donate those lone pairs. Yeah. Now with deactivators, meta directors, right? The atom that's adjacent to the ring have that positive charge, or they have no lone pairs. NO2, that's a withdrawing group, right? But if you expand it, it's N double bonded to O, single bond to another O. It's a positive charge, so it it always has a positive charge. So that's a withdrawing group. Looking at all of these, the central atom never has any lone pairs, right? They either have a positive charge or no lone pairs at all. So that just means that they are withdrawing groups, right? Withdrawing groups, they are deactivators. The only weird thing here is halogens, right? We always have something weird. Halogens, they have lone pairs, right? You have 6 lone pairs, or 3 lone pairs, 6 electrons around the halogens. They are deactivators, but they activate orthopara. Okay. The reason why is because they can still donate those lone pairs even though they are withdrawing groups. And here's our overall table of your substituents. The right side being strongly activating, and then left side strongly activating, then right side strongly deactivating. You can see here that the strongly activating has those lone pairs, right? And then your halogens are the weird one where they do orthopara. Here's another table, same thing. Okay, now what if you have multiple substituents, right? If you have multiple substituents, it will try to satisfy all the substituents or the strongest activator. Right? Also consider check engines. So for this one, we have NO2, which is the activator, CH3, which is an activator. So it doesn't care about NO2 because that's a deactivator. It cares about the strongest activator, which is this one. So strongest activator at ortho para, but ortho is the only one available, so it'll add over here. But it is also meta to NO2, so it actually satisfies both substituents. That's good. Everyone's happy. Now for this one, we have a withdrawing group and a donating group. Because this is a donating group, it will try to satisfy this substituent, so orthopara. So here, you can attach here, here, or here. But because this is sandwiched between these two substituents, it is less likely to attach here. So here, it's either one or two. They are equally likely to attach, so the major products would just be the meta or the right ortho position. And then with adding, if you want to add R groups, right, here's where phenol crafts come into play. Phenol crafts, remember, it is the AlCl3 and a R group with a chlorine. Now, R group with a chlorine, it just adds the R group when you have the phenol crafts. Remember, the phenol crafts cannot happen on deactivated rings. So once you have a deactivator or a withdrawing group like this, doing field crafts will not happen. Okay? So if you want to add your R group, make sure you add your R group first, and then add your withdrawing group. Yeah, so here at the bottom part is just there's different variations. You have AlCl3, FeBr3. They're considered field crafts. So as long as you have that R group and the alkyl halide. Right? Now, if you want to add a ketone, right, it's just an acyl halide where you have the carbonyl next to the chlorine, and you can add it that way. Remember, they cannot react with deactivated rings. Right? Now, the trick with Fieldcrafts is that, well, actually, this is another way to add R group. Okay. For if you want to add another R group, another way you could do it is get an alkene and react it with HF. Now, what happens here is this alkene will become a carbocation, right? It becomes your electrophile. Now, your electrophile can now be reacted with the benzene ring and make an R group attached to the benzene ring, right? And F is just there to deprotonate it and make that, reform the double bond. Okay, let's see. So for here, another way to add an R group is using an alcohol on it first. So if you start off with an alcohol, right? If you want to turn this into a good electrophile, right? We use BH3 or HF, right? And it will basically turn this alcohol group into a good leaving group. And once it's a good leaving group, we can form that electrophile right here, electrophilic R group. And once you have that, you can add it to your benzene ring. So, right here, if you have alcohols, if you want to add this onto this ring, we would react it with HF. This HF will remove this OH, making a positive charge in this center carbon. And now, because this is a donating group, it will attach to the pair position. Pair position right here, and we said there's a carbocation on the middle, and so it will attach just right there. So you have a isopropyl group. Or you can attach on the ortho position as well, right? Okay, so another thing is with field crafts is that when you add just a regular alkyl group, it's going to, when it forms that carbocation, it will undergo rearrangement. So let's see. Yeah, right here. They can do rearrangements. So let's see. If you have for example, we have if this is your Fieldcraft molecule, or actually, not that. If you have a Fieldcraft like this, right, and you want to add that to your ring, when it forms a carbocation, when it turns into an electrophile, your positive charge will be here. But that's not the most stable position. It's actually at the center carbon. So it will do a hydride shift. Right? And it will attach at that carbon. So instead of your ring looking like this, it will actually attach like this, right? Because we have that rearrangement. Okay. Now, if you want to prevent that from happening, what you could do is make a carbonyl next to that chlorine, right? That prevents it from doing a methyl shift or hydride shift or any rearrangements. And you'll basically make a ketone right here. You make that ketone, and once you make the ketone, you can do your Clemmensen reduction and remove that ketone. So you have your R group, linear R group attached to your benzene. Okay, and then with electrophilic substitution out of the way, now we have nucleophilic. Does anyone have any questions about electrophilic aromatic substitutions? Okay, now nucleophilic aromatic substitutions, kind of like, it's kind of like the opposite. Now with electrophilic, that's when you add stuff to the benzene. Nucleophilic is when you substitute something from the ring, benzene ring. Now the requirement here is that your benzene ring needs to be deactivated. Yeah, we need electron withdrawing groups, right? We also need a leaving group as well, right? Because substitution requires a leaving group. So for this one, it's kind of the opposite, where now electron withdrawing groups are now orthopara instead of meta, and donating groups are meta. So in this case, here, this is really deactivated, right? You have two NO2 groups, right? And we have our leaving group right here. Now, because it's now deactivated, we can do aromatic substitutions. So we have NH3 here. We can add that this amino group. Adding heat and pressure is going to substitute this leaving group, Cl, with NH2. Right. So what if you don't have electron withdrawing group, right? But we want to still substitute this Br. Well, what we can do is, we will do a benzene reaction. So using NaNH2, what happens is what's weird about this reaction is that you create a triple bond on the benzene ring. Okay, so the NH2 negative sign will deprottonate an H, and something weird happens here, right? What happens here is we kind of make a elimination reaction where this Br leaves, and it makes a triple bond right here. Now this triple bond is really unstable, right? And what's going to happen is that NH2 will add on to either one, right? They're equally likely to attach on either side because it's just an alkyne. So you'll have your NH2 either on the left side or the right side. Right. Now, if you want to add R groups to the molecule, another way you could add R groups, replace leaving groups with R groups, is using organocuparates, right? So we have an R group right here, and CuCli. CuLi here. Remember, we can't just do field crafts to add R groups. Remember, field crafts, you can't do field crafts on deactivated rings. So if you want to add R groups, you have to use organocuparates. So you'll just add the R group on the, you'll replace the leaving group with the R group here. And then another reaction to replace leaving groups with R groups is using this Heck reaction. Right, here we need palladium catalyst and a base. So what happens is you have your leaving group here. It just replaces the leaving group and attaches this alkene on the side where the alkene ends, so the terminal side of the alkene. So if we use it on a benzene ring with a good leaving group, it will attach at the tip of the alkene, right? As long as we have that palladium there and a base, this molecule will replace that I and attach it where the tip of that alkene is. So we'll add just like this. So that's the Heck reaction. Now the next one is Suzuki reaction or Suzuki coupling reaction. Right, now with this one, it's kind of similar to the Heck reaction where you're adding R groups, replacing leaving groups with R groups. Now with this one, we still have that palladium here, right, in the base. So that's still the same. The only difference is you have a boron in there. So with this boron, it just, when you react these two together, it replaces the X, or the leaving group, with the R group that the boron is attached to. So if we have something like this on the left side, we have that good leaving group. We have another reactant, but it has that boron here, boron in there. And we still have that palladium and our base, right? Water is still a base. It's going to add the R group that's attached to the bromine. So instead of that bromine being there, it's going to be this benzene ring. So like this. And other aromatic reaction is we have the catalytic hydrogenation, where if we add H2 and a lot of pressure and some catalyst, metal catalyst, we can completely change this benzene into a regular cyclohexane. Right, we're just basically forcing hydrogens on there, making sure we remove those double bonds. Now what if we want to keep double bonds, but we just want parallel double bonds? Right. We want one on the right. Now what you need to do is need liquid ammonia, so an alcohol and a metal, so like NaLi. Right, this is, you can kind of tell it's a Birch reaction because it's the only reaction that has liquid in it. So when you see something liquid, especially if it's ammonia, it's going to make this benzene ring into a diene, but instead of it being conjugated, they will be parallel. Now the orientation of that depends on your substituents. So here we have our Na and then ammonia, along with our alcohol. We have electron withdrawing groups here, right? Now, they repel double bonds, so our double bonds will make sure it doesn't touch it. It doesn't touch that substituent. So the only way that could happen is it's orienting kind of like away from it, But if it's a donating group, it will try to touch it like this. Right? That is your merge reduction. So what if you have a electron withdrawing group or electron donating group in the same molecule? Right, it'll try to satisfy as many substituents as it can, but typically I would try to satisfy the electron donating group first. So if you have a carboxylic acid or on a ether on the same molecule, I'll satisfy the ether first and make sure it touches the electron donating group. Now this is kind of pretty easy, right? If you have any R groups in your benzene ring, if you add KMnO4 or any chromate stuff, it will turn those R groups into carboxylic acids. So here, no matter how long it is, it could be 1,000 carbons long, it will turn it into carboxylic acid. So this one turns into carboxylic acid, same one on the right. And then here, if this is kind of another weird one. If you have a chromate and you have that alcohol there, it will. If you have an alcohol on your benzene ring and you try to oxidize it, it's going to add it'll turn it into a ketone, and it'll add a ketone on the opposite side of it, and will also turn that benzene ring into a two parallel benzenes. Yeah, that should be it. Does anyone have any questions on 17? Good. Okay, did you guys get a practice problem set at all? Okay, well, we can go over that.
By the way, does everyone have a copy of that problem set, or do we need that? Okay, I got a pass the paper around for everyone to sign. I can send it to everyone. Where is that paper? Okay.
Yeah, we can take a break. We can take like a 15-minute break or so, 15 to 20 minutes. We can meet again at 5:40. Say that.
And if y'all need your names on there, send them on here. I'm just gonna make a big team.
That's absolutely
It's funny. Yes, we'll send out the PDF with all the problems. We're also gonna be sharing them on the board, but I know
that's the music. It is kind of funny.
And if y'all want to name down,
Weird.
It's
It's a huge number of lessons you can ask us. It's right. My sister does a British accent.
It's a bunch of different ones. Hey, are you good? Good. So we're trying to be done by 7 by people saying this. If you do have to head out, I am setting up Yeah. We will listen to it. I am interested in so as long as
The way he goes like through like the reactions and stuff, he doesn't really tell us he'll like explain like the reactions very briefly and then he'll do like the shots and then he'll also the names.
I'm gonna set it up. Oh, is there? That would be great. Okay. Well, it's so good to have y'all sign it. We will just send it on. Sorry about that. Always a
Watching
question.
someone else like very
No, so y'all should receive it for. I'm just gonna put everyone on this Teams message. Yeah. Sorry about that. Or, how about we make this volunteer? Can everyone use QR codes? We're gonna do that. Let's see. Okay. Frank, a proposition. If I make a QR code for the problem set, can you put it on your laptop?
Johnny was taking the camera roll. I did. Sorry.
When do you more? Right now, like, everything will be a lot. Yeah. I mean, I'm so for the best right now. Oh no, it's only spring semester. Shit. It's like for now. I'm just trying to survive each week. Yeah. Yeah, it's getting it's okay. I really last year I did better than he told me that he told you that you caught him out and I told him that you told me and told him you gotta go. Oh,
I found it.
okay.
Oh,
But this semester was
okay. If you can open that QR code on your computer, I just sent a message here to you. Everyone should get access to the PDF, which is easier than me trying to send it out to everyone.
Where's it?
I sent it to you, so it should be the other one. Oh my God, is it loading? Hold on. Give me a second.
Yeah.
There it is. I thought it was on.
It should be sent there. Yes.
I think it goes. Good resume, right here, which drops the one there to bond right here in the and this double bond goes over which makes this negative.
There you go. QR code.
I will not forget.
Save that. I can't send that to her. She didn't save it.
You weren't having to carry it. Slide off this. It's not gonna happen.
It's good. I'm glad that we didn't ask the questions yet. I think that's mostly strategy and problem. Oh my God. People are asking those comments that I'm like, I don't know. They were hopefully.
I want to learn.
Because I made one of my friends actually, the password is so long too, so that they could check, not the check, I have them open
My
the
password
setting
is
to make sure that it can be opened by people who have not been shared with us.
Okay.
So I think it should work. Yeah, I think it's just hard on weekends because we don't have like leather related to it. Huh? Do you want to do the problems?
He's literally
I can do half. Okay.
He's on fire.
Where did he get that from?
I can do ranking. Okay, now.
It's a great game.
I was, I hadn't really looked at it,
Oh, Rosa, but you played it, you haven't seen the April Fool's event, have you?
I think it was there. Honestly, I don't remember anymore.
I hated it because look at this shit, look at their faces.
That's true. Like this
This super ass.
Why do you have so many cookies?
Because I love this game. So starting to think there's probably a reason why it's trash. So yeah. Can you imagine that finding a video game in trash with all your friends and it's anime ass? I think it'd be horrifying. Listen, we will get you one day.
I'm just like bending.
I'm so mad because they did the worst podcast sorting out. They put me into the
Honestly, I'm fine.
they put me into the cream knife.
Okay.
Okay. I started the recording, but it started after like.
Oh.
She's fine. And okay, please.
Can I get?
Okay.
It's just and then it's you. And then a Fox and then my daughter's terrible shirt. And then, but yeah, just, I don't know.
That's crazy.
More calculus. Which is what makes it makes me weird.
Right. That's something like.
Why is this worse? Why is this worse?
And then I'm gonna get stressed.
It's like, I said 540.
540? Do you mind if I use your laptop? I can otherwise. No? Okay. We can just swap. It's a weird Sunday. It was a tornado one.
Yeah.
That is. I have been playing about this. Do you want to know one of my childhood memories that went into my brain? Is that we like, I think it was like 6th grade, there was one project that researched about a country, and this one person was researching about Japan, and they were just, the applicants were talking to them, and they just turn around and look and pick me in particular. Everyone knows, hey, this is girl, and I just happened to know exactly their name and everything. Okay, thank you. It's like, they looked at everyone in the room and said, that's the nerd that knows about anime. And that hurt. Oh my god. Which one? That's the canon. Well, the other team had one too. This is what I get for trying something
Let's circle the ones that like do
I know, I'm gonna ask you because I don't see what people say.
Okay, I was just about to do that. Do you remember that one? You said it. I made a lot of promises. Yeah. So. Stop. Have you seen those ones? Have you seen those ones where it's like, this person has made you so they won't get a notification because you're driving? Please send this. It's urgent.
Or.
Did you tell her that and she handed it to you and then she took it back?
This is fancy. Okay. No.
I'm sorry. I would just say that. Why would I say it's like if anyone ever said to me they want to be a travel, I would walk away slowly. It's not a good thing to want to be. Santa, you gotta take your D1 medicine.
Yeah.
Yeah. I was thinking that there was like a outside, but not.
Actually, I can probably do, I can do the stuff on this computer. So if you want to take your computer,
I'm not sure.
I can maybe teach the session on the projector.
Or we can do it right here. Is that different?
This is the actual.
Oh,
I feel very, very sad.
that's why I think I've been doing is do put it on OneNote so
Uh-huh.
they won't mess with it.
Okay, we could do that. Let's do
I
that
mean,
then.
that's a separate issue. Instead of two different presents.
That will still help. I was just like, trying to see what to make it easier, and I also don't want to necessarily steal your laptop, but
Oh, yeah,
if
that's
that is
fine.
fine, I guess that will also be good, so we don't have to spend
Share screen. Let's do this. OneNote.
Okay.
Or actually,
I have my own little sheet. Not that I need it.
okay. Let me. This one, this one.
No, it's not.
Duplicate 2 and 3.
Okay.
Two changes. So now. For that. Oops, okay.
Sounds good.
So red.
Yeah, I'll probably just use one color.
Okay. Erase, okay. Okay, cool.
So eraser and sounds
Yeah,
good.
that's good.
Okay, I'm gonna seal this one. Okay, y'all, we're gonna get started. Yeah, I think we're unmuted. Everyone got a chance to pull up the PDF? Okay, otherwise we'll be sharing the questions on screen, so you can always look at them. We'll also be posting a recording of this entire session on YouTube, probably on Monday, with the slides, the problem set, and the problem set key. So those are all going to be available later. Okay, so let's get started. We're just going to go through some of the ranking questions. You're going to see quite a few of these on the exam, and they're all just going to be really testing one of three things, which Frank really talked about: conjugation, aromatics, and knowing that those activating versus deactivating groups, right? So let's take a look at this. For our first question, B, I guess, we're going to be ranking by lambda max in UV, in the UV visual experiment. So for R1, that is going to be our largest lambda max, while our compound with the shortest wavelength will be number 5. So my first question to everyone is, a larger lambda max, what does that indicate? What did you say? More conjugation. Perfect. More conjugation and actually lower energy difference between your HOMO and LUMO, right? So we're going to be looking for more conjugation for our number 1, less for our number 5. So 1 equals most conjugated, right? So does anyone want to give me my number 1 or my number 5 based on that?
What was that again? So we're saying the first one would maybe be 5. And which one is 1? Second one is 1. Right. So how did you choose those? So the first one does not have conjugation, right? Conjugation you identify by looking for those alternating double bonds versus your number 1, everything is conjugated. You actually see 3 aromatic rings, right? Can someone else give me 3, 4, and 5? And you can take a second. I'll give you a minute. 5 will say, think about conjugation, and then also think about the number of substituents on your double bonds. That will also help you. The one in the middle? So 2, we've got conjugation between these 2 rings, but we don't have any in the middle. It's a good one for now. Okay, what about those last 2, 3 and 4? Okay, the one on the right, 3. Okay, so we both have like conflicting answers on that one. Or no, wait, we've got the same answer. I just can't do directions. So we agree, this is 4 and 3. So I know we went through that a little quickly. Does everyone agree with that? And just to give a broader reason why, number 1, you'll see is fully conjugated. Everything sort of is an aromatic. Number 2, we sort of said you've got 2 aromatics. And number 3, you still have some conjugation. Whereas 4, there's isolated conjugation. 5 has none, just like we said, right? Let's take a look at the next one. Oh no. Yes, I'll use the mouse. Okay, so also letter B. So we're going to be ranking by the rate of reaction for an electrophilic aromatic substitution. So again, my first question is, when we're talking about ranking an electrophilic aromatic substitution, what are we actually ranking? What are we looking for in these molecules? Because like it's very fancy to say, like I'm looking for like how reactive it is, but what specific features? The stability of the sigma complex, right? And what does that indicate? Like what does that make our aromatic good at being? Yeah, so we're looking for a good activated aromatic with a stable sigma complex that will act as a nucleophile, right? Because remember, when you say electrophilic aromatic substitution, it's a bit of vice versa, where you have your aromatic acts as a nucleophile attacking an electrophile, right? So in this case, we're looking for that activation, right? So let's take a look at this. We've got a bromine substituent on one of these, NH2 on the other, an amide, right? Which I'm just going to circle, and sort of vice versa. So we have NH being the connecting group versus our carbonyl. So any theories for where we should start going with this? So when we're looking for activation, are we looking for electron withdrawing groups or electron donating groups? Donating, perfect. So of these, let's start with that. Which of these are electron donating? NH2. And the third one also has that, amine group right adjacent to the aromatic, right? So both of these are electron donating groups, right? And the others are electron withdrawing of varying ranges. So let's start with those first 2. So electron donating groups are obviously our best bet. So between NH2 and having our amide, which one would you choose as number 1? Amide? Why would you choose the amide?
So NH2 versus the amide?
Uh-huh.
You pick the NH2
Okay, so we would pick the NH2. Why would we do that?
because it's a lifelong.
Yeah, so we picked the NH2 because both of them are electron donating, but our NH2 does not have a carbonyl on it, right? So that carbonyl is going to make your substituent overall a little more electron withdrawing. You know, it's sort of weakening the power of that. So we're going to put our NH2 as number 1, amide as number 2. Okay, so does anyone have a 3, 4, and 5 for me? Look like you're counting.
3, 4, 5.
So you're saying first one 3 and then the last 2, 4, 5? Well, let's take a look at that. So we've got bromine, our carbonyl, and then an NH3. So why do you do that order?
BR is less deactivating than the carbonyl,
Mm-hmm.
and the NH3 has positive charge.
Right. So if you have a positive charge, that's going to be super electron withdrawing simply because it's electron deficient right now. So your NH3 is your number 5, and Br tends to be on sort of that middle spectrum between electron donating and electron withdrawing. The way I like to remember it is while bromine is electron withdrawing, it's also an orthopara director, which is sort of like, okay, like it can't really choose. It's like not quite, you know, electron donating and not quite electron withdrawing, right? So we can put that as our number 3 and our carbonyl as our number 4. Everyone agree with that? Any questions? Okay, we're going to move on. Let's take a look at this. And now we get to number 1. So we're going to be ranking by stability for this one. So we've got some rings, not necessarily aromatic, but we're going to have to decide that. So I'm going to give everyone a second to take a look at these structures and decide whether they're aromatic, non-aromatic, or anti-aromatic. I'll give you until 5:52. And I'm just going to pull y'all while you're like working. Is everyone mostly feeling good with aromatics? Are we feeling a little more confident coming into the exam? I remember when I first like learned about them, I was like, I know about benzene. Don't tell me about any other ring. But you know, they all follow the same rules. After you get some practice, they're not too bad. They're not too scary. Okay, it's 5:52. Does anyone need more time? I'm going to go with it. Okay, so first one, aromatic or non-aromatic or anti? I should not say all of those. Someone call it out. First one, aromatic. So we've got 6 pi electrons. Everything is conjugated, and we have a planar ring. So that's good. Aromatic. What about the next one? Anti-aromatic, so we've got 8 pi electrons, still 7 members, so it's planar, but not good, right? So anti, what about the next one? non, right? It's not conjugated. Next one, non, and last one, aromatic. But a little interesting, right? So how are we going to start that ranking? So we said ranking by stability, right? So typically that trend goes, which one is our most stable, aromatic, anti, or non? Aromatic, right? And our least stable is anti. I like to tell students it's like the death code. You know, like that's when you see that, it's like it's done. It's unstable. You're not having anything happen, right? So just based on that, we can put that as our number 5, right? But let's look at these aromatics then. Which one are we going to choose as our most stable? Right. So why would we choose the one on the right, or the one on the, which one? The inductive effect. So we have induction. Okay. And thus that negative charge is delocalized. That's good. So we've got that. Took me a second too. But yeah, so we're going to choose that as our number 1 because we have an inductive effect on our negative charge. Negative charge is, well, pretty good on a aromatic ring. We still don't like a negative charge on a carbon. So it's still like, you know, not quite the vibe. So when we have inductive groups, that's always good. So that makes our other aromatic number 2. And between these other 2, which one would we choose? I think this is interesting.
Would it be 4 and 3?
So I'm hearing 4 and then 3. So why are we choosing this non-ring structure as number 3? Conjugation, right, perfect. So even though not really a ring, really not aromatic, it is conjugated. And that's really important. Even though number 4 has resonance, it's not quite as good as a properly conjugated set, diene. Okay, and we have one more ranking question. Let's look at this. So we're going to be ranking by uranium ion stability, which is also our sigma complex. So the uranium ion is lowest in energy for 1, and we're looking for something that's super unstable for 5. So when we're saying more stable uranium ion, what are we looking for again? Electron donating or electron withdrawing? Electron donating, perfect. So we're looking, and so like this is where you're going to realize that actually most of these questions are sort of testing the same knowledge. It's like electron donating, more stable, sigma complex, electron withdrawing, less stable, and then they have some specific characteristics to them, right? So let's go through this one. We said our first one should be mostly electron, like we should have a lot of electron donating substituents. So all of these have a bromine on them, right? And we have our positive charge. So can anyone give me my number 1? I can give y'all a second. Actually, let me give y'all 2 more minutes to just take a look at the question and solve. We will look at it at 5:58. Giving everyone a couple last seconds. Is everyone mostly done? Seeing some nods. You can also raise your hand if you want some more time. But okay, let's take a look at it. So again, we're gonna do what I've been doing for all of these ranking questions. Can someone give me either 1 or 5? So either most activated or most deactivated. The first one is 1. So I see we have an amine, an amide off the ring, but the connectivity is by the amine, right? And we have it placed in a meta position, but it looks good. So yes, so we put that as our number 1. Do we see anything more stable, or is that our most stable one? Most stable? Okay, let's take a look at the next one. Do we have a number 5? The 4th one? So in this case, we have what is it? We have 1 electron, 2 electron withdrawing groups. Perfect. And we also have this positive charge in the meta position to an electron withdrawing group. So that makes it more deactivated. That's a better position to put our positive charge on. What about our next one? Our like 2, 3, 4. Sorry.
Would the rightmost one be 2?
Mm-hmm. And then what about our 3 and 4? How do we want to compare those? What's the difference between them? Yeah, so on one of them we have this electron withdrawing group right here, sort of a red flag, right? Versus this one doesn't have anything. So what is our ranking going to be? 4, 3 or 3, 4? 4, 4. Oh, I heard both. Anyone want to give their views? Okay, why do you say that? So the electron withdrawing group makes it less stable. Perfect. So we're going to have this as 4 and 3. And I believe that is our ranking. Everyone good with that? Makes sense?
How's the first one? Like, compared to the second one?
Oh, so 1 versus 2. I will say, Frank, do you know why 1 versus 2 are the way they are?
So when you resonate your positive charge, the first one, the positive charge lands on the carbon directly connected to the electron donating group. And whereas the one on the very right, the positive charge only ends on the ortho position of that electron donating group. So because we have an electron donating group, having a positive charge right next to it will help it resonate that positive charge to the donating group.
Or delocalize electrons across that. Thank you. It's
Yeah.
been a while since I've seen these questions.
I mean, two people in the SEC.
And so, can you repeat that?
They said that the carbocation would be meta to the original position. So, for example, the first one would be not directly connected to the carbocation, the donating group, it would be next to the donating group.
So think of this as you're adding that bromine So pretend the bromine isn't there, right? So you just have those groups on the top. So when you grab the bromine, first one, that's in the pair position, right? And donating groups, you like the pair position, right? So that's why that bromine is added to the pair position. Whereas the one we're going to write, the bromine is in a meta position, right? The electron donating groups, which is that amide, is ortho pair directed. But we have it added to the meta position. So that's why that is less stable than the pair position of that bromine. So that's another thing about it. This is the uranium ion stability, so it's the sigma complex intermediate. So before you do the elimination reaction to complete the benzene ring, you're just ranking it by the intermediate of the carbocation. Yeah.
Basically, just look at the positioning of where we're adding the ER.
Yeah, basically. So that's another way to think about it. But what Ria was saying, yeah, if you do resonate that positive charge, you want to keep that positive charge away from
Electron withdrawing.
Yeah,
groups.
electron
Right.
withdrawing.
Basically, you don't want to make it more positive. You want to make it more just normal, not positive or negative. Okay. And I think after this we have Diels-Alder.
So we can finish with them. No.
Okay. Yeah. And we'll also do another sort of aromatic question. So let's take a look at this. We have some compounds that will dehydrate readily in acidic conditions. So basically, if we were to pronate one of these oxygens, or the alcohol, we're going to see the formation of water, which will leave. So when water leaves, does it leave a carbocation or a carboanion? Positive or negative charge? What did we say? Positive, because it's taking away its electrons with it, right? So we're going to see a positive charge. This is different from, for example, acidity ranking, where you're going to be using a negative charge. So just something to be clear on, aromatics change a lot, whether you put a positive or negative charge on them. So do be careful with that. So we're going to basically be replacing each of these OHs with a plus, right? And just going through this, we're going to circle which of these dehydrate readily in acidic conditions. So how can we determine that? What are we going to be looking for? Going to be looking for aromatic stability, right? So we're going to be looking for aromatics or just some kind of stabilizing effect for these positive charges, right? So let's take a look at this. This first one, we have a positive charge on a cyclopentane with 2 double bonds. How many pi electrons do we have? 4. So you've got 4 pi electrons, and what does that make that? Anti, right? What about our next one? Six pi electrons, perfect. And so anti or aromatic? Aromatic, right? All of these are conjugated and cyclic, so we don't have to worry about those. We're really just looking at the pi electrons. What about the next one? We've got some lone pairs on this oxygen, which can make it a little spicy. Uh-huh. 6 pi, right? So we count all of the unhybridized p electrons, right? So although this oxygen has 2 sets of lone pairs, we only count one of them, which is going to be in the unhybridized p orbital. So that's aromatic. What about the next one? Got boron. Does boron have lone pairs? No, right? Boron is happiest when it has 6 valence electrons, but it can take on a charge. It can resonate. So in this case, how many pi electrons do we have? 4. So that makes it anti, following our pattern, right? And let's go through some of these next ones quickly. So this one, anti or aromatic or neither? Anti. So how many pi electrons does it have? 6. That's correct. You have 2 sets of lone pairs on the oxygen and nitrogen that apply. That means you have 6 pi electrons. We said anti or aromatic?
I messed up. It's aromatic.
Aromatic. Okay. What about the next one? Okay. Does everyone agree with that one? Well, doesn't really matter what anyone else thinks. I agree. It's 8 pi electrons. Did everyone get that? Okay, so that's anti. Okay, what about someone else? Can someone tell me what the next one is? Aromatic. That's aromatic. And what about our last one? Trick question. Non-aromatic, right? But what does our positive charge have on that one? It has resonance, right? So although it's not aromatic, it's not anti, which is like that killer that we talked about, right? So based on that, which ones of these should we select just broadly as they will dehydrate readily? All the aromatics, right? So we're going to select this one, this one, this one, this one. And here I have a question for y'all. What about this one? My error is bad, but it's okay. Yes, so we're also going to select that one. So even though it's not aromatic, resonance still helps stabilize that positive charge enough that it's an allowed conformation. Really what this question is just asking is, can we stabilize that positive charge more than an anti-aromatic? Let's take a look at reactions. Well, Frank's going to be doing our reactions. These are for you.
All right, so, should I answer? Yeah. All right, before we move on to reactions, see if we have any questions. Okay, give me a second. Okay, before we go answer the questions on the problem set, I do want to show something that could possibly be helpful. So I used this when I was in Okay, but there's an app called Mechanisms, right? It's kind of like a little game, but if we go on to the electrophilic reactions, it kind of tells you like how these mechanisms work, and you can like it's like a puzzle basically. It's called Mechanisms, right? It is not free, but there's a like a free version, I would say, yeah. But here, let's go over one of them, right? So we have this benzene ring. You have AlCl3, AlCl2, right? So basically how this works, you have you can like move these electrons around, and it'll tell you if it's wrong or not. It even if there's also a video. If you click on that triangle on the very bottom right. If you want hints, they do tell you what to do in here. But so, but let's get into with this, right? So we want to make the Cl2 an electrophile. Now the AlCl3 is there to make it an electrophile. So what happens is this Cl kind of attaches to the Al, right? So keeping that electrons with it. Now we have now we made the Cl the electrophile. Now, because of that, this benzene can now grab that Cl, right? And then now we have that Cl on the benzene ring. Now, remember, we still want to do an elimination reaction to complete that benzene ring again. So we have this H over here. So now the AlCl3, that is our Lewis base, right? So it's going to, one of the Cl will grab that H, right? And now it's kind of like a decision point. Does that H, it wants to remove that negative charge, so it'll return it back to that, return it back to the C and connect it to the H, to the carbon again. So now we have our chlorine, benzene, right? Oh yeah. There's other ones too. So let's do one more before we do the our problem set. So let's do something like phenolcrafts. I think this is phenolcrafts. Right. Okay. Now, what do you guys think will happen first? Or what do you want? What do you want to do? I'm sorry. Yeah. So basically, yes, we want to make this molecule here a electrophile. So the AlCl3 is going to help it become that. Oops. Right there. Oops. Okay. Now we have that electrophile. Now, what happens next when you have that positive charge there? Do we just directly connect it to the benzene ring? Or do you think it undergoes any rearrangements first? What do you think? And if it does rearrange, what kind of rearrangement? Anyone? Can it do a hydrate shift or a methyl shift? We have a primary carbocation. Looks like we might do a methyl shift, right? Now what is it on? Tertiary, right? So now, yes, now we can add it. Add that. And remember, we want to complete the reaction with an elimination at the base. So, grab that. Oops. And then form that double bond again. Cool. So yeah, so that's kind of the basis of like all of these reactions, the aromatic reactions. Remember, there's always a base to complete the ring again. And remember, we're always trying to make an electrophile. Okay. Well, let's move on. So if you want to look at all of these reactions, you have other things. You have how to react NO2 or sulfonic acid, adding onto the ring as well. And for the next exam, you're going to deal with aldehyde and ketone reactions, carboxylic reactions. So I would say it's a pretty good investment. So let's see. Okay, let's move on to the actual problem spec. Okay, cool. Let's do this problem. The first one. Okay, so we have what looks like a diene and HBr. What other information they give you that stands out? Yeah, 40 degrees, right? That's pretty hot. Normally, if it's cold, they're gonna give you something like something negative. But it is a hot. What does that tell us? Yeah, thermodynamic product. So let me draw this. Okay. Okay, so whenever you're adding on to dienes, what happens? What's the first thing that the dienes do? Okay. Sorry, I'll give you a hint. The diene can act as a nucleophile. So what does it take from the HBr? Does it take the H or does it take the Br? Let's say it'll take the H, right? H is the positive part of HBr. So remember, we always want to make the most stable carbocation. So the H will end up over here, and our carbocation will be in this tertiary position. Now remember, this is thermodynamic, so what do we do when it's thermodynamic? Do we just add the Br onto the carbocation, or do we try to resonate that positive charge? Did you resonate? Yeah, resonate that. And then your positive charge will be over here. And now you can add your Br over there. So your final product should be like that, right? For thermodynamic control. Okay. Now if you guys have any questions, just feel free to just raise your hand. Okay, let's do something. Let's do Yeah, let's do B, right? Looks like, what kind of reaction do you guys think this is? Is this a aromatic reaction, or looks like a Diels-Alder, right? You have Diels-Alder. So when you have this, you have a diene, a dienophile. So we have our substituents pointing inwards. So first, let's draw our basic ring. Right. There is if we number it 1, 2, 3, 4. On 1 and 4, we have those two carbons attached. They're pointing down, they're pointing inwards, so they are going to be wedges. Right, you would draw them like this. And then now we have our dienophile. We have carboxylic acid on both sides, right? But remember, carboxylic acids are withdrawing groups. So does that, following the endo rule, would that make them endo or exo? If we have carboxylic acids. Endo, right? So with this right here, we have a dashed carboxylic acid, right? But because this is trans, right, stereochemistry has to be the opposite. So it has to be a wedge. Okay. Now let's do something different. Let's do E. So looking at E, I'll give you guys like 2 minutes to try to figure this out. This one? Oh, this one? No, there's just a single bond. Sorry, that's supposed to be. I was just highlighting it. Yeah. But part E, part E. I guess 2 minutes.
Okay, and this could be a displacement on the end. So these are being activated that are under the surface. If you're looking for something like this, that can be done and has pi bonds with pi elements. Right. So, carboxylic acid does. So the only reason that in this case we have to put one of them on the wedge is just because they're trans to each other, so it's required that you keep that at the end. However, typically you just put that on the gas.
Okay, that makes sense. What is your noise really difficult, but maybe I can sense to it. You can give us a good reason, right? So,
Yeah, I did.
okay, so it goes with right?
Yeah.
So the way to think about it is this conversion of data and that one that can come down from something like this. Because as soon as it's rational, what is it actually? Because of the basis of speaking,
So the oxygen.
yeah.
So the way I like to tell people is that if you see an oxygen or an nitrogen, both of those are carbon.
Right.
So they look to the carbon fixation. So so the carbon adjacent to it is Fe2, then they're going to keep it pure. So that's what it's going to be. So even if you're not entirely worried about some positive charge or derivatives, as soon as oxygen is dialysis, it changes as we said, it's also
Cool. That was like the thing that
if there's a negative present,
yeah.
yeah, so that always occurs with oxygen. They will always follow the thing. But like the decreasing presence, they're really high. So, and that's just because I've got some easy ways to do that.
Okay. That's all I have.
Yeah, ask us any questions.
Okay. Let's start on this. So here it looks like you have excess HBr. Now, to go about this, remember, a lot of these reactions are nucleophiles attacking electrophiles, right? So on the one on the left, what is electrophilic about? No, what is nucleophilic about this molecule? Okay. Now, here we don't have double bonds or anything, but we do have lone pairs. Right? Remember, lone pairs can act as nucleophiles. So here it can actually attack the electrophile part of it, which is the H. And then giving that H, the electrons to Br. Now we have an OH positive. Okay. Now it looks like we made an O positive. Whenever you see an O positive, that's going to be something like a good leaving group. So it looks like we made a good leaving group, and we also made another nucleophile in the process, which is Br minus. Right? So you have a nucleophile and you have a leaving group, which is the OH positive. So now we can just attack it on either side. So we make two products, the OH and the O, or actually just one product. So we make something like this. Now we keep doing that since we have excess HBr. So another HBr is right here. Remember, we always want to do a nucleophilic and electrophilic. A nucleophile will attack the electrophile. So we have two places where you can attack the H. Let's do the ether still. Okay. Attacks the H. And then you get first part, which is this. Oops. Okay. Now it looks like we made another leaving group. So that Br that we just made can do another nucleophilic attack, either over here or over here. But let's go over here this time. Now what we just made is BR OH and BR OH. So they're pretty much the same molecule, right? It was just flipped upside down. So as you can see, this HBr will keep giving H's to the oxygen. And whenever it keeps giving the oxygen an H, it makes it a good leaving group. A good leaving group for the Br to substitute. So you can predict now that this OH can get substituted again, right? We have the, we'll add on the H, makes it an H plus. Now this whole thing is a good leaving group, making the Br attack this carbon here. So our final product is actually this one. We would have 2 moles of that. Okay. Let's do an aromatic reaction. Let's do J. Okay. So we have this benzene ring, right? Now it has 2 substituents. Are they? Let's look at OCH3. Is that withdrawing or donating? Donating, right? Yeah. So it has lone pairs right here. Donating, and then we have this R group here. Now R groups are also donating, right? But compared to OCH3, which is stronger? Yeah, O group, right? The OCH3 is stronger because it has those lone pairs ready available. So because it's the stronger donating group, that means it's also a stronger activator. Right? So we want to satisfy that. So orthopara of that is it'll be here, here, and here. But it looks like the para position is occupied. So are we only stuck where we are stuck with the ortho position? So we just pick one, right? So let's say the bottom one. So add that BR. And yeah, that should be your final product. Okay. Okay. And then here, this is kind of like one of the last reactions I was talking about for part K. This is we have a boron here, right? That is going to be our Suzuki reaction. Remember Suzuki, it's that we have that boron in there, where when we have that PD and a alcohol, we're just simply adding the R group. We're replacing the leaving group with the R group. So here's our leaving group, and we have our R group. That's what R. Okay, so yeah, you can just directly replace it. Yeah, so that should be our solution right there. Makes sense? I kind of just like flipped it, so but it is the same molecule. Okay. Let's see. Now let's do something with a NMR, or yeah, an NMR table. Okay. So let's look at this problem. It's problem number 7 on the last. So I see here benzene is reacted as shown on the scheme below. They're shown the HNMR of B is shown. So we have 2 doublets, 7 at 7 and 7.5. We have a CNMR which shows 6 peaks. And yeah, and then what is A, B, and C? So it looks like A, we can just do a simple reaction, right? So we have a benzene and looks like a field craft. So I'll give you guys like 1 minute to go to do A. Okay. Okay, so now remember, with phenol crabs, the AlCO3 will remove that Cl, putting a positive charge at that carbon. So have a benzene ring and the carbocation, just right here. Now, is this the most stable carbocation we can make? No, right? So because of that, we can do a rearrangement, right? So that can be we can do a hydride shift because we still have a hydrogen here. Putting that carbocation over there. So we have a tertiary, everything is stable. So now we can get that, we can use one of the double bonds here to get that electrophile. So now your A should just be that, right? Just add it to the center of that tertiary carbon. Okay, now A to B, they do give us a reaction, right? Br2FeB with FeBr3. Let's look at the NMR that they do give us. Now here, this is a electron donating group, right? The R group over there. Now it just wants, the reason why they gave you HNMR is you don't know if the bromine was added here, the pair position, or at the ortho positions. So the HMR is there to kind of tell us that. So it looks like we do see the 9 here, right? That's the 9 for the T-butyl. And then from 7 to 8, that is our aromatic range. We have a 2 and a 2, right? And the only way we can have 2 pairs of similar hydrogens is to put it in the pair position. Is either one will break symmetry, right? Yeah, so right there, where these two are equal, and then these two are also equal. Br and T-butyl. Okay, and then the last part. It looks like we're adding Mg and then a alkene with a bromine attached to it. Okay, so adding that Mg, whenever you add Mg to a molecule that has Br, it just turns into a Grignard reaction. Or it turns into a Grignard. So that's just a simple reaction where instead of Br, remember MgBr. Okay. Second step, now we have this alkene with that bromine. Now, whenever you see Grignard, I usually think of it as the R group that it's attached to. The carbon will have a somewhat like a negative charge. So you could really write it like this with a negative charge over here. I know that's pretty unstable, but the MgBr is there to stabilize it. Now this is a nucleophile, and here we have a molecule with a good leaving group, right? So this is kind of another nucleophile electrophile reaction, which is really common in these chapters. So It's going to attack that carbon, making that bromine leave. Finally, our molecule should just be like that, where it attaches to that the allylic position of the alkene. Right? That makes sense? Okay. Let me do one more question. This, yeah, we will post a key as well, so you can look over all these questions, use it as an exercise. But I do want to go over, let's see, I think it's this one, yeah. Kind of just like breaking the basicity of aromatic rings. Right, so I'll give you guys, say, 3 minutes for part A. Yeah. Okay. So let's look at all these rings. So for so we're asking you to rank these rings by electrophilic aromatic substitution. So remember, electrophilic aromatic substitution, we want activators, right? Activators will help it go through electrophilic substitution. So let's look at ring A, right? So we have an amide. Now, is this a electron withdrawing or donating? Donating? Yeah, donating. So that's good. So that's donating. Just write it down. Okay, ring B. So looking at, it looks like it has substituents on pretty much all of it, right? So here we have an R group, donating or withdrawing. Right here. Donating, yeah. How about this, the other side of the amide? Is that Donating or withdrawing? Yeah, withdrawing. Okay. How about these benzene rings? Are they withdrawing or donating? Donating? Yeah, I agree. Yeah, they do have, you can resonate electrons towards um, the ring. Right, and the last one, what would you say this is? Donating? Yeah, I would say it would be donating. It would be slightly donating, yeah. And C, looking at C, right, it's attached to this ring. Now, would you say this ring is donating or withdrawing? Donating? Yeah. It's also donating. And then the last one, it has 2, right? So you can say that the same ring is also donating. How about F? Is that donating or withdrawing? Yeah. Now let's rank these. So let's see. Let's look at the ones that has only donating, right? Because we want only donating for our electrophilic substitutions. So the only one that has donating is ring A and ring C, right? Now we just have to rank which one has a stronger donating group, right? So we have the nitrogen over here versus a aromatic ring. Which one would have electrons readily available? Yeah, nitrogen. So ring A would be 1. Ring C can be number 2. So that's 2. So now we have B and D. So looking at B, it has donating groups, but the main difference between B and D is the donating group or the withdrawing group for B is that carbonyl right here. And the withdrawing group for D is this fluorine, right? So which one is the stronger withdrawing group? Carbonyl, yeah. So carbonyl is a stronger withdrawing group, so that means it strongly deactivates it compared to the one with just the fluorine. So ring D should be number 3. B is 4. Right? Right, and then yeah, and then B. Why is the rank the fastest for electrophilic aromatic substitution was chosen? Remember, it's because should be A, yeah. So it should be A. Okay? It's because we have those electrons at nitrogen, and it's an electron donating group. So yeah. Does anyone have any other questions? If you do have other questions, feel free to stay behind and we can answer any questions that you have. And yeah, the queue will be posted and the video and the slides should be uploaded to our YouTube pretty soon. Should be either tonight or
I think by tomorrow.
tomorrow, yeah. Okay.
That's